So the presentation time is 30 minutes, including questions and answers. So please welcome Anqi Liu with big applause. So the stage is yours.
Okay. Hello, everyone. This talk is crafting your own Numpy, do more in C++, and make it Python. I'm Anqi Liu. So I will introduce a bit about myself. So I contribute a lot on open source, and I use the ID as Tiger Cosmos. I'm from the Taiwan community called SciWork, which is composed of a group of Taiwanese scientists and engineers. I'm also a maintainer of the PK++ project. I'm now a software engineer in Mugen in Tokyo, which is a robotics company. I'm also writing a new book, which is talking about some software essential in Mandarin and will be published in Taiwan. My hobbies is snowboarding and photography. So if anyone are interested in anything listed here, I'm willing to talk with you. Okay, so why do we need to make a new array? So array is a very fundamental component everywhere in any libraries. Usually we would like to add a lot of features on top of arrays. And in your project or in your libraries, usually there are a lot of components, modules that will interact with arrays. And making your own array can have a better integration with your modules and arrays. What's more, if you make your own array, you will have a better memory management. And speed is the king. We will always want to write code fast. But we know that Python might not be the fastest one because Python is interpret language. It will not be as fast as compilation language like C++, Java, Golang. So, but we still like Python. I believe everyone here likes Python. So we know that C++ is fast because it can leverage the compilation, optimization. It has static check. Usually it will run much faster. But Python is easy to write. We only need to write a few lines of Python code, but we need to write 100 lines in C++. So Python, we can implement very fast, and we can do quick prototyping, which is very easy to use. So we have a dilemma here. So we want Python's simplicity, but we also want C++ optimization. Actually, we can have both. So we just let Python to drive C++ code. We can do it by using Python plus C++ plus Python 11. And we can do that. And then by doing this, we can have more flexibility and more efficient to manage the memory. If anyone has joined last year PyCon APAC 2023 in Japan, this was a talk called Write Python for Speed, provided by Dr. Chen. He demonstrates more basic concept of Python binding and the use case. But this year, I would like to introduce more engineering details. So first, let's take a look how we use NumPy. So when you use NumPy, you just call numpy.array or numpy.arrange, and you define the dtype int 32, 64, or even complex number, and you can just get the array. You see we declare a dtype here because dtype as a data type is very important because we need to know the data type and the information of the data so we can calculate the correct offset in the memory. So we can get we can correctly access the elements in the array. Then I would like to introduce how we write the Python binding between C++ and Python. So on the slide is a simple array definition in C++. You can see we call the array simple array. You can see there's constructors. There will be some methods, including like size to get the size of the array. And there's a member. We have the size here, and we also have the data, which is the row buffer. I just use std vector here as the row buffer. And you can see I fixed to use the double type here. I will talk about this later. And on the PyCon 11 part, PyCon 11 is the library that we can bind C++ code to the Python part. And so in this definition in PyCon 11, so we just bind the C++ simple array class to the Python object called simple array as well. And you will define some constructors, and you will also define other methods and properties. And then you just finish the binding. PyCon 11 itself is not hard to use. And then we can get a result at the below part. So you will see how we use it on the Python interpreter. And we just import simple array, and we create a new array, and we can get the size of the array. And the underline is actually in C++. But we just mentioned about the D type. So where's the D type? We haven't implemented yet. So we want to have the D type in the array, just like what Numpy does. And to do that, for the C++ developer, it will be very straightforward to use the C++ template. And then we can give different types into a template, and we can have different types of array. For example, if we have a template array called simple array with the type T, and you will have simple array int, simple array float, or any other type. And this is the example of the template array. So it's pretty much the same as the previous definition, but you can see at the beginning we have the template definition. And you can see at the bottom we changed the row buffer to std vector with the T type. So the type here could be int, float, or untyped integer. And we can also bind the template array into the Python. So here I define the helper function called add type array. It's also very similar to the previous definition. But you can see now we bind the template array to the Python. So if we bind the int simple array, then the Python object will code simple array int32 and so on. So for example, if we bind the float, then it will be simple array float32. And the result will be like this. So then we can have a different type array. And then we can introduce what's the D-type challenge. So you see in Numpy, no matter what D-type we give, no matter int32 or float64, and you will see the type is always numpy.nd array. It's always the single type. But we just demonstrate how we write the type array binding between C++ and Python. And we just create a different type. So you see we have simple array int32 and we have simple array float64. They are clearly different type, which is not what we want. We want to be like as Numpy. So we are missing a single array, simple array, and that can take the D type as argument. We want to do a triplet. And we can see how does Numpy do. So in Numpy, when you create an ND array, the underlying C definition is actually an object called PyArrayObject. And in that object, there are many fields, but the most important ones are the data and the descriptor. The data one is the pointer of the buffer memory, which store all the elements of the array. And the second one is the descriptor, which describes all the property of the data type. And we will use that data type to calculate the correct offset in the memory. And you can see the below part is the descriptor definition. So it is called PyArrayDescribe. And in this struct, you will see some properties like what's the kind Is this integers or floating number? What's the type? Is int32 or int64? Or the byte order? Is this in the C style or Fortran style? And the most important thing here is the element size. So we know what's the size of the data. So then we can use it to calculate the offset. And here's the example. So I just create a NumPy array here, and we can just print the D-type information. And we will see for the int32 D-type, the array.dtype is int32, and the character of the dtype is I, which means the integer, and the byte order is the symbol means the C style bytes order, and we also get the item slice. And you may wonder a lot why we just not use the NumPy approach. Because yeah, obviously our NumPy approach will work, but there are two reasons. The first one is in our library we already defined the type array at the beginning, so there's existed code base, and we want to have the new single array type with the D-type argument on top of the existing code base. And the second thing is we want to leverage the C++ advantage. So we know C++ has template, for example, and template is very useful. It sometimes will simplify a lot of code. So we want to also have that benefit. To achieve the D-type, you may think, oh, then it's very simple. We can just make it in the Python because Python is powerful. It can do anything. So we just have a wrapper on the Python side. And you see, I just defined a Python class called simple array with the data and the D-type. The data here is like a data holder will hold the array. And in the constructor, you will see, yeah, I just have the D-type in the argument. Then we can down our requirement. So if the D-type is int32, and then we just create the simple array int32 instance and put it in the data holder. If it is float64, then we just create simple array float64. And we just create different array based on the different data type. And of course, you can have other setters, scatters, and any properties or matters, and based on your underlying type array. And yeah, it works. So as you can see, we just get we give different D type here, but we always get the same Python type. It works, but it's not very ideal because there are some drawbacks. So the first thing is, if we implement something on the Python side, then we just lose the static check from the C++ compiler. And we want to have that because static checks is very helpful. And the second thing is, we just mentioned that if you put some code on the Python side, it will sacrifice some speed. We don't want to lose some optimization from the C++ compiler because we want to write a very fast array. And the last thing is, if you put a wrapper, which is Python, if you put a wrapper on the Python side, then you have the array on the Python and also have the underlying array on the C++. And then you will have the memory management issue because no matter what, because we are doing the array library, so we're supposed to have a lot of memory accessing. Then if you have both Python and C++, then you need to manage the memory between Python and C++, which will also make the code more complicated. So we don't want to do that. So that's why we want to implement the wrapper just at the C++ side directly. After some investigation and some experiments, finally we make a purge in the mod mesh library. So I would like to introduce what's the approach we finally choose. So on the C++ side, we create a class called simple array plex, which is like a wrapper as previous in the Python. And in this class, you can see we have the dtype argument, so it can accept the dtype. And we can have other constructors, but we don't have any methods of the array because we're supposed to get the methods from the type array. And there are only 3 members in the class. The first one is the flag of the ownership. The second one is the pointer of the instance, which will store the type array. And the last one is the data type. The data type could be int32 or full64, for example. And here I demonstrate what the implementation looks like for a constructor. So you see we have the dtype here. And we will see what's the dtype. For example, if it is int32, and we just create a new simple array int32 and store the pointer to the pointer holder. And we will use this pointer later. Then we can go to the PyCon 11 part. So to make the PyCon work, first we need to create some helper function. So in this execute callback with type array callback function, you see there are 2 arguments. The first one is the array plex, which is the simple array plex type, and we have another callback. The callback will define how we use the type array. So for example, we read the array plex and check its type, and here we check if it is int32 type, and if it is int32, and then we just get the type array from the array plex. We use the pointer holder that we just created, and we cast the pointer to the correct corresponding tab. So for int32 data type, it will convert to simple array int32. And I just mentioned we have the callback function. The callback function defines how we call the type array. So if the callback function defines to call this function, we just pass the type array into the callback, and the callback will call the function in the type array. And here's the example in the PyCon definition. So you see, we just bind the C++ simple array plex into the Python object called simple array. And of course, we will have the constructors, and you see we have the data type here. Then we will, of course, we will implement some methods. So I would, so here, for example, if we have the onBody method, which is a custom method in our array, and because now we are in the array plex, but we want to get the method from the type array. So we just use the helper function we just created. So you see, when the onBody is called, then we use this helper function to code the underlying type array's onBody, and we return the result back to the Python. Then we don't need to implement any methods on the array plex, but we implement it in the type array. Yeah, so far everything is good. We just finished the implementation, but there's that piece. So I mentioned that we are creating a new array based on the existing code base. So then we will encounter an issue that there's a type array in the original code base, and we just introduce new array type. So to let both array types working together, we also need to implement a casting mechanism. So we are able to cast the array plex to type array, or cast the type array to the array plex. Luckily, we can do it in PyCon 11. So PyCon 11 allows you to do some customized casting. You just need to implement the type cast template under the Python 11 detail namespace. And you will implement some logic to casting. The principle of the casting is somehow more complicated and out of scope of the it is out of scope of the topic, so I will just skip the detail. But if you are interested, you can check the source code later. So finally, we'll just make it. So you see, now we have a simple array with a different D type, int32 or float64. They are different type. And now we have the same data type in the Python side. And I just mentioned about the casting. So for example, here we have the array flags with the type int32. And we can just code that typed to cast it to the type array. And the operation is actually very cheap because the underlying data, we don't do any modification or copying for the underlying data. And it's the same for casting the type array to array flags. And of course, we want to have the same method between array flags and the type array. And so in our implementation, you can, for example, you code the getter or setter, it will be the same. And all the property will be still the same. And any methods that in your array will be also the same between the array flags and the type array. And here's our project. It's called ModMesh. It is a toolkit to dealing with the partial differential equation. The project is still under development, but if you are interested about our implementation details, you can read the source code in this project. And to sum up, we want to write very fast Python. And to do that, we can use Python to drive C++. And then we can have a very fast, powerful array library. And thank you very much.
Thank you. So we have a 5-minute Q&A session. So if you have any question, please raise your hand.
Yes, please.
Sorry, I may have missed it there at the end, but did you do any performance comparisons?
You mean compare with pure Python wrapper and a C++ wrapper?
Yeah, for instance, or a Numpy.
We haven't done the benchmark or performance check, but we try to do the thing we think is right.
Thank you.
Is there anyone else?
Let me know the official support of Python to C++. My experience, C interface to C has already micro or compiling automatic tools. How about the official support to C++? This is your own system?
Sorry, I think I didn't get your question. Could you
This tool is your own development.
Yes, yes.
And there is another official support to C++. Only you? Only one?
You mean if there are any alternative libraries?
Yes.
Okay, I see. As I mentioned before, people always like to create their own arrays library because you have the most flexibility, you have the full control. So at the beginning, we don't consider to use other tools because we want to build the things from scratch so we have anything on control.
In your implementation, the simple array has an attribute called typed.
Yes.
It returns the actual type of the specific type. So from the viewpoint of the user of that language, is there any useful way to use it, or is there such a similar method in the original Numpy?
You are saying about the example here? Yeah. So the type here means casting the array flags to type array. So it's not getting the data type. Do I answer your question? Sorry.
Yeah, right.
I think I don't understand your
Is there
question.
any accepted use case of that kind of method?
Oh, I see. So as I mentioned, we have original code base. So in the old code base, we use a lot of type array. So we just want to have a casting system, so we can let the type array and the array class using together. That's why we need to have this kind of implementation to be allowed to cast from each to another.
Thank you very much.
Yes.
We still have 2 minutes.
Yes.
Do you have an example of Python level user code using mod mesh?
It's not on the slide, but you can see how it's really pretty much similar to how you use NumPy. So you can see it's an alternative of NumPy. But because we implement, it is a toolkit to solve some encryption. So we have other modules. And yes. So the purpose to create our own arrays library because we want to have a better interaction between our other modules and the array. So yeah, of course you can also use NumPy, but you still need to have some wrappers on top of it, and that is not efficient. So we decide to make our own.
It occurs to me that the difficulty of this work is really, and what NumPy really provides, is the encoding of the computation into the array and the extensibility of the D-type mechanic and the promotion rules. For example, in your previous slide where you talk about modeling this naively in pure Python, what you'd be missing there is the promotion rules. So when you implement any arithmetic operation, you have to figure out how to promote that properly, which is very complex. And probably, for this case, you just use float64 uniformly anyway. Because you're doing PDE solving, right? So you're just using, there's no promotion rules involved in the simulation.
I'm not sure what the promotion means here.
You take an int32 array and a float64 array and you add them, what do you get? It gets promoted to float64. So there's very complex rules inside NumPy for determining how to do multiple dispatch on the inputs in order to get the output. So that doesn't seem to be modeled either.
So are you talking about some type check?
So if you think about it, for any binary operation, you do multiple dispatch on the left-hand side and the right-hand side to figure out what the output would look like. NumPy will do that internally with some very complex rules. That's why it needs to know, for example, not only is it int32, but it's an integer subtype.
I see. So as we implement the core logic in the C++ side, so I think that wouldn't be an issue because C++ is a strong type. We have static check also. So we do also check a lot of about the data type in the C++ side. So yeah, if we implement on the Python side, it will be a little difficult, but because we implement in the C++ side, so I don't think that will be an issue. I think you are talking about the bytes alignment or something. Oh no. So you are talking about the how to deal with the element data type. Yeah, so that wouldn't be an issue because on the C++ side, everything are typed.
Okay, so thank you very much for your talk. It was very interesting. Anchi, thank you.
Thank you very much.